Hi everyone, thanks for staying through to the last section of this presentation. My name's Dave Madge and I represent our discovery business in Europe. Today I'm going to talk a little about the current status of virtual screening as a hit finding strategy in our organization. As you will know, virtual screening is a collection of computational techniques we can use to mine very large libraries of compounds to prioritize them for further evaluation, which might include further computational evaluation, acquisition, or synthesis. One important aspect of this technology is, of course, that the molecules we screen using these approaches do not need to exist as real samples. In fact, they may never have been synthesized. So we can apply a computational selection tool to imaginary molecules in order to decide which ones might tell us something interesting about interactions with the target protein, and may therefore be worth synthesizing. Such virtual libraries can be very large, many billions of molecules, and can also be very diverse, encompassing large areas of chemical space. We can apply these technologies based on our understanding of one or more ligands with the target protein, the relation of a collection of known ligands to each other, or sometimes just based on our knowledge of the three-dimensional structure of the target protein. Of course, we will usually want to follow up on a virtual screen by carrying out a real measurement of the biological activity of the molecule. Hence, there's been a lot of interest in the creation of so-called make-on-demand libraries. These are virtual libraries based on the enumeration of known chemical reactions using available scaffolds and building blocks. And consequently, there is a realistic expectation of fast follow-up, making real samples available with good success rates. One way to think about this is that virtual libraries store a huge amount of nascent information on small molecule protein interactions, information that can be revealed using virtual screening platforms. So as the computational tools that enable screening of large virtual libraries have improved, enabling screening of larger libraries in shorter time periods, so have the size of the virtual libraries grown, limited only by our creativity, and in particular for make-on-demand libraries, the availability of building blocks to include in virtual library enumeration, whilst retaining reasonable access to the real molecule. High-throughput searching paradigms for such large virtual libraries are becoming very established. And this figure refers to work carried out by John Irwin and colleagues, docking around 100 million make-on-demand small molecules against the AMP-C beta-lactamase and 140 million against the dopamine D4 receptor. For both targets, new high-potency chemotypes were identified from the huge chemical space being screened, with nanomolar and even picomolar actives confirmed in biochemical assays. These results were backed up with real X-ray data, which showed a strong correlation between the predicted binding mode and that confirmed by crystallization across multiple ligand types. In parallel to the year-on-year increases in raw computational power we've all come to expect, there are increasing applications of machine learning to support an even faster application of virtual screening techniques. By applying machine learning, we can rapidly build predictive models based on smaller data sets, which we can then apply to much larger data sets rapidly and with a high degree of consistency and accuracy. This means we can screen ever larger virtual libraries in the same time or less, scanning chemical space encoded by billions of structures. A recent example of the transformative impact this can have is shown on this slide, from a study using machine learning to model the relationship between structure and antibiotic activity. A neural network was trained on about 2,000 known molecules, whose activity data was collected and then classified simply into active or inactive, and used to train a deep neural network. The model was augmented with molecular features computed by the RD-Kit tools, resulting in a receiver operating characteristic curve, or ROC, area under the curve of about 0.9, demonstrating the highly predictive nature of the model. The model successfully identified and classified further known antibiotics from small data sets, and was also used to screen 100 million small molecules from the zinc data set, identifying novel molecules with confirmed in vitro antibiotic activity. To reinforce this trajectory of larger libraries and faster docking performance, a recent paper describes the use of a deep docking approach. This work was based on a deep neural network utilizing QSAR models trained on actual docking scores of a small subset of a compound database. and then predicting the docking scores for the rest. This circumvents the need for vast computational power and makes screening of billions of molecules feasible from both a time and a computational power perspective. High ROC values were observed across multiple targets, demonstrating the scope and usefulness of this strategy. It's often suggested that there may be 10 to the 63 possible drug-like molecules. And so, of course, we cannot construct a virtual library to represent all of those compounds. Hence, we need to perceive ways to explore that space from a much more focused starting point. One strategy that is attracting increased attention is to combine generative machine learning models able to carry out in silico design of new molecules based on a set of chemistry rules, with virtual screening based on an evaluation of fit to a structure or pharmacophore. We can then envisage an iterative in silico design and docking cycle using feedback and retraining of the generative model to help us explore chemical space that the algorithm creates. In doing so, we can also incorporate additional filters that use predictors of other metrics, such as basic physical chemical properties, DMPK properties, and toxicity prediction. This machine learning-led strategy gives us a new tool to discover novel molecules that were never part of any real or virtual collection. This slide provides a slightly more detailed description of this workflow, which can start from virtual or real hits and uses a combination of different representations of the active molecules, such as molecular fingerprints and feature vectors, to train a deep neural network and enable this multifactorial property prediction and molecular optimization approach, driving generation of new molecules we could not have conceived of by other routes. So to close this section of our discussion, virtual screening forms one part of our comprehensive toolbox for identifying and optimizing chemical matter for new targets. We can envisage matching each platform to the target of interest based on the target type, tractability for different platforms, and pre-existing knowledge. But it's also worth considering how we can combine the application of more than one platform and create a much more diverse and comprehensive collection of starting points for drug discovery by evaluating more chemical space, including generating completely new chemical space for our targets. Many thanks for your attention.